quantum good software targets them. So if we define it, it eventually will need to be implemented by multiple people. And the only way to do that is to get the microarchitects on early. They usually come on quite late, but it's too late once the specification is out in final review. We want them on early, and as I said, we need all three levels. The architects are great, but the micro-architects need to be in there. And some of the discussions that you may have seen on the ISET at this overall this year are more geared against that people think, well, I don't really think this is a good idea, or it should have been done differently, because it's going to impact my microarchitecture. But once we're in public review, it is usually a bit late. So we need to get that feedback cycle early and see that we get the definition just right for a large consensus of the ecosystem. Thank you.
Thanks a lot, Phil. Next, I would like to introduce Kirill Colette. He is the Director of Information Sciences and Techniques Research Group at Thales Research and Technology. This group focuses on disruptive technologies such as embedded and trusted AI, open hardware, continuum computing, quantum computing, in order to facilitate their adoption and integration into future Thales products. And I'm very excited to hear what Thales has been doing in open source hardware in the last 4 years. Thank you.
Okay, so first I want to thank the committee to invite Thales and to invite us to present what we are doing on RISC-V, and we will present our experience since 4 years. We are working on RISC-V since 4 years, and I want to congratulate the organization of this conference. If I am correct, the first edition was 5 years ago at Minatech, and when I see this audience and the number of people and the number of presentations at this event this year is very impressive. So thank you and congratulations for this. And thank you for you to be there after the social event, the great social event yesterday evening. And I will, I hope you will be present to understand what we are doing under RISC-V. So to introduce my presentation, so I will speak about I will speak about applications, because we want to use RISC-V processor inside our system. So I will explain to you why we invest on RISC-V, on what are the interests for us to have this kind of processor, especially at the European level. And before that, I want to give one message. Okay. This is a photo of my PhD. So I was quite lucky during my PhD because I worked on the processor architecture. We designed our own processor. We make some parallelism around this processor. We had the chance to work and to do a lot of things in this domain. So it was very good and very instructive for me. And this period will be over. Has been over after this at the beginning of this century, because we have the hegemony of Intel processor on ARM processor, and it is not possible to have access to the infrastructure of the processor. And when you see the CVR6 processor, it's a great opportunity for the students and for the lot of people to work inside this architecture, to make some gardening inside this architecture. So it is a new opportunity, and this is very important for the European ecosystem to be able to work on this. Okay, and another point, another thing I want to point out is the fact that in the previous decade we had two revolutions running in parallel. The first revolution was on IT and the computer science with the HPC, and there is another revolution dealing with the embedded part with the OT system, operational technology system, and these two revolutions run in parallel without connections together. And since 10 years with the IoT, we are able to connect the two things. And we are able to connect the HPC and the IoT. And it is a new revolution because we are able to make these connections. And for us, for Thales, that means we are able to address new system, to design new system with these strong connections. I'll give you some examples. In the domain of the sea, under the sea, in the domain of the Navy, you have a lot of connections between the different elements under the sea, on the Earth. So the system are strongly connected. Another example, in the domain of the battlefield, the soldier now is connected to a lot of information and is connected to the information coming from the other soldier and for the headquarters. So this is very new, and in the past our system was designed separately. Now our system must be designed with strong connections. Another domain is the domain of automotive. We are very present in the domain of cyber security of the connections between automotive. And last week we go through a high level of certifications in this domain, and of course this domain is also strongly connected. And another domain is the domain of airplane, with the capability to have the full connections between the plane, the satellite, and the Earth. And another domain, of course, is the satellites with a strong connection with the Earth. And the last domain is the constellation of satellites, because you have to manage many satellites together, so the systems are strongly connected. And to do that, we need to be able to manage the continuum and trustable computing solution. That means in the past we designed separate computing solutions without connection. Now the whole system must be continuous and trustable. This is very new, and this is something very important for us. What that means? That means we need to have system with high level of autonomy. We need to have system with low power in order to be able to have a small system. The safety, of course, is very important inside this system. The cyber security is also, and is very important. And the two domains, safety and cyber security, are quite orthogonal, so we need to manage both these two properties. And the interconnection is very important because of, as you know, the connection between those systems. We have to manage this and to be able to deliver trustable solutions. And the continuum computing from the cloud to the IoT and from the IoT to the cloud must be managed. Okay, and to go just in detail, I will pick up an example in the domain of AI. Okay, you know the domain of AI is well known, and we have a lot of data coming from the sensor. This is the machine learning. The problem of this statistical AI is these solutions are not explainable and are not trustable. It's why we need to have a cooperation with symbolic AI, the old AI based on the model, which is a very explainable, and we can have the capability to deliver trusted solutions. So we have the composition called the hybrid AIs, and thanks to this we are able to make optimization, decisions, inference, and we are able to embed this in the system. And when you are, it's the algorithm point of view. When you think about this algorithm point of view, you know that some characteristic of the architecture may be able to be implemented in the architecture in order to be able to run this kind of application. And as I say, in the system before, we have no connection between the IT and the embedded system. Now we have a strong connection between IT, HPC, embedded with the new element in the system called the edge computing. And this element is very important. And we have to face and to design this system, and for Thales it is important to ask the question, is there any opportunity to have RISC-V processor either at the embedded level, either at the edge level, and either at the HPC level? Excuse me. Okay, so it's why we think about RISC-V. When you introduce a new technology, you need to have differentiator, and after that you need to have enabler. Concerning the differentiator of RISC-V, we can say that with the RISC-V or open source, there is no vendor locking. There is capability of sovereignty, and we can share the cost due to the open source community, due to the business opportunity for support and customizations, and due to the possible commercial exploitations without export constraint. For our business, this point is very, very important. And this kind of approach is a good opportunity for the public authorities, especially the Europe, to invest in this domain and to create an ecosystem. And another main differentiator is capability to be able to manage the swap, that means the size, weight, and power, the customization of the architecture, and able to add some specific instructions, for example, for the artificial intelligence, in order to manage the safety, which is very important, and in order to manage the cyber security. And to manage the cyber security without export constraints. This is very important. And for this, okay, we extract fit, we have the exact fit between the feature and the application needs.